hello, 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 hello. Hello, 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 hello. I don't know if the live is working or not. Hopefully it is. Welcome, welcome, welcome. Good morning, good evening, good afternoon, good night, good everything to everybody who is about to join. We are live. I am going live after some time tonight to talk further about Baji and physics. This is the channel. Here is Baji right there. Excuse me. Baji is over there sleeping, and we're going to talk about physics. So therefore, this is the Baji and physics channel. So tonight, actually, it's nighttime here in the Boston area, which is where we're streaming from. Tonight, we're going to talk about cosmic rays, which falls under particle astrophysics, which is my background. And in past videos and past episodes and past live streams, we have actually mentioned quite a bit about particle astrophysics, what it really means, what it even is, and things like that. And we're going to continue with that topic tonight, but specifically we're going to focus on cosmic rays. So that's what ahead of us, that is what lies ahead of us tonight. Hopefully I will see many of you joining the live stream here and now, and be able to wish you a good evening, good night, good morning in person right here as we stream. Or if you're seeing this as a video upload later on under the live tab of this channel, then welcome, welcome. Thank you so much for joining. Thank you for watching, and please do leave us a comment. Always appreciate seeing your messages, comments, chat messages, all of the things, all of the thoughts. Please do share. And there is Baji for people who are asking about that. So sometimes I have been noticing that people have been going onto my older videos and asking where Baji is. And so I wanted to point out a few different times during this live where he is. He can be very still, but he is there in the background. So before I continue, let me go and make sure that all the settings of this live are actually good and working. So let me go do that as I continue to stream here tonight. And if you're joining, please do say hi in the chat. That helps me to understand who is here. And please do like, share, subscribe. Hello, welcome, welcome, welcome. I see somebody sending emojis and likes. Thank you so much for joining. Thank you, thank you, thank you. Thank you for joining, and thank you for sending the likes and shares and the hearts and the emojis. Thank you. Hey said something. Hello, hey, how are you doing? Hi, Angelito says hello. Hi, Angelito, Angelito. How are you doing? Destiny says hi. Hi, Destiny. Hey, hi, everybody. Hello, 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 hello. I'm about to share the live from my other device and make sure all the settings are good. So we're just getting started. Please do like, share, and subscribe, and please do say something in the chat. Really appreciate you are really appreciate that you're here. Destiny says hi. Destiny Mikado says hi. Hi, Destiny. You look amazing, by the way. Oh, thank you. I don't know if that's your username or if you're telling me that, but thank you so much for being here, and thank you for the compliment to me and the whole universe. Thank you so much. Destiny says, how are you? Hi, I'm good, Destiny. How are you? Angelito or Angelito says, how was your day today? It was good. It was really good. Actually, I got some work done, and then I went to the gym, and there did I make a new friend today? I think I made a new friend yesterday, not today. All the days are good, thanks to the universe and thanks to God. Destiny Mikado says, nice to meet you. Nice to meet you. How are you doing, Destiny? How is everyone doing here? Say something in the chat. Please do like the live as well. Please double tap the screen, and that will give us a like. Where are you from? I'm in the Boston area in the United States. Where are you from? Gamer Raja is saying, where are you from? I'm originally from the great nation of India, but currently I'm in Boston. That's actually my name in, okay, Arabic. You can call me Haider. Hi, Haider. How are you doing? Destiny says good. Okay, so yeah, I was talking about my day today, and then we will talk about physics, and we will continue to say hi to everybody that joins. If you want a shout out of your username or anything you want to say in the chat, please do go ahead. I try to read every comment, every chat message, everything like that. So thank you for being here. Please do like, share and subscribe. Tell your neighbors, tell your relatives, tell your cousins about this channel, and have them to join as well. Feeling great. What about you? I'm good. I went swimming tonight. I did my set me out or shut me out, says Destiny Mikado. Hi, Destiny. There you are. So I went swimming. I did some weightlifting. I actually it kind of hurts under my arms right now because I did the same lift 2 days in a row, and I thought that would be fine, but actually I kind of really felt it tonight at the gym. And then I did my swimming, which is my reward for lifting weights, which you know, I am not as big of a fan of, but I do like the results of lifting weight and feeling stronger and becoming stronger. But and then when I was not doing so well a while ago, just a couple months ago, I actually had taken a break from the lifting and the swimming and all of that. And that was a little tough because I really like swimming. It's good for my mental health. So the more I can get back into it, the better. I really appreciate being able to do that. So did that, did the hot tub, did the sauna, did the showering, took the bus, came home, made some new friends slash, actually, I have some bus friends. I see them on the bus. These are my bus friends. And coincidentally, I met my bus friends when I went out to eat. Small world, right? Small world. Boston area is a pretty big world, one would think. But actually, turns out, when I went out to eat with my friends, we went to a lunch buffet in this area. And lo and behold, guess who I see there? Guess who I see there? Same friends that I have made on the bus. So these people also take the bus. Hi, hello, Gamer Raja is saying, yay, you looks, India, great manners. Thank you, thank you. I try to have great manners, but I am definitely from India. That is where I was born. For sure, can confirm. Lionheart says, you have nice facial features. Oh, thank you, Lionheart. I love the username Lion. I want to raise a lion. Destiny says, did you been Six Flags Magic Mountain? I don't think so. I don't think I've been to a place called Six Flags Magic Mountain. In my country, it's like 7:32, says my new friend. So 7:32 in the morning. Is that right? The morning, so no one's awake. Bro, you look like you were born on your birthday. I love that. Parabolic curvature says, bro, you look like you were born on your birthday. Yeah, dude, I was born on my birthday. Believe it or not, I think I was born on my birthday, and my birthday season is about to start very soon. In fact, it has already started according to my calculations. I like to celebrate my birthday for 2 months, 30 days prior, 30 days after. And we are now very much in the window of my birthday. My birthday is coming up soon. It's in October. I'm a Libra. And I have already started to celebrate in September itself. So at any point now, you may feel free to wish me a happy birthday. Thank you so much. Thank you. Angelito is laughing, crying. Oh my gosh, wow, parabolic curvature. Parabolic curvature has done a super chat of $2 for me. Oh my gosh, well, thank you so much, my friend. Oh my goodness gracious me. Thank you so much for doing a super chat. I really appreciate you, Parabolic, and I love that username, Parabolic. Hyperbolic. See, some people are hyperbolic, but parabolic is parabolic, and I love it. A parabola. Just a beautiful curve is a parabola. So thank you for the super chat. Norin Rad is my favorite character of all time. I do not know who that is. I'm so sorry. I don't know too many of the Western shows. I grew up watching Bollywood and Hindi and Indian film and TV shows, and I still don't know a lot about America. It's no excuse because I've been living here for forever. So you might have to tell me who that is. Destiny says 9:35. So underrated, says rewrites history. So I'm not going to say the first thing, the Google thing, because 9:35 is so underrated. So underrated, says rewrites history. So I'm not going to say the first thing, the Google thing, because 9:35 is so underrated, says rewrites history. So I'm not going to say the first thing, the Google thing, because My Google Mini here always lights up whenever you join the chat. Acacio, my friend. Hello. Acacio59, hola amigos. Hola, 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 ¿cómo estás? How are you doing? Acacio, I haven't seen you forever. It's my fault. How are you doing? So how old are you is asking how old I am. Destiny, can we be friends? Of course, we already are. Parabolic says, may the power cosmic protect you. Oh my gosh. Well, thank you so much. Thank you, thank you, thank you. I do have this prayer that I habla español. I just know a little bit of Spanish for my Hispanic friends here. But you feel free to teach me more and say anything you like in Spanish. That would be most wonderful. Most bellissimo. No, bellissima. I think that is beautiful in Italian. I know that that's not Spanish, but that's what came out of my mouth right now. Thank you so much. And Destiny says Porterville, California. Is that where you're from? Are you from California? I'm not super familiar with California other than San Francisco and San Luis Obispo, actually. Destiny's from California. Goodness, how is that great state doing? Very long and very big of a state indeed. Hermosa says rewrites history. I don't know what that means, but thank you. And I was going to say something that I forgot. This rewrites history. I think you've been here before, am I correct? And usually we hear from my Google Mini whenever you join. Acacio is saying, I am doing great now that I finally catch you on a live. Oh my gosh. Thank you for being here, Acacio. We are live. Oh my gosh, Lover Toy Pops. Hi. Hello. Lover Toy Pops. My favorite dog channel is here. Destiny's saying you need to visit Six Flags Magic Mountain. Oh, is that in California? Oh, is that what you're saying? That in California there is this Six Flags Magic Mountain that I haven't been to that I should check out. You are correct. You know, California has a number of things that I need to check out, including but not limited to those big trees. I really want to see the big trees in person, and apparently this magic mountain flag thing. That would be most excellent if I can get the opportunity to do exactly that. Thank you, Destiny, for the recommendation. Beautiful in Spanish is hermosa. Oh, hermosa. Is that beautiful in Spanish, Acacio? Acacio, can you teach me what is beautiful in Spanish tonight? In fact, can you teach me, well, bien is good. Can you teach me beautiful, lovely, amazing in Spanish? BJ! Oh my gosh, my friend from South Korea is here. Hello, my friend. How is South Korea? We usually don't meet so often on the live, but BJ is here. Oh my gosh. I can't say the rest of his name, so I just say BJ. Sorry, it's I know he's from South Korea. Let's see. Lover Toy Pups. Apparently, we share the love for cats. Lionheart, we do. I love cats. My children are cats. I birth cats. They come out of me constantly, and I love them so much. They are my entire universe. Destiny says, yes. Lover Toy Pups. Send hearts. Thank you, please. Can you please, can everyone please like, share, and subscribe? If you're not subscribed, please do subscribe. Can you double tap to give us some likes, and can you send some hearts? That would be most amazing. We have Six Flags Great Adventure. Destiny says, very Six Flags Magic Mountain Fright Night. Oh, is that so? Is that a thing? Is that an event? Stephanie says, good morning from Germany. Oh my gosh. Hermosa is beautiful. Okay. I had no idea that hermosa is the word for beautiful in Spanish. Goodness, that is a very beautiful Hermione, Hermosa. I'll try to remember that Hermione Granger, my favorite character from Harry Potter, similar to that is Hermione, or not Hermione, Hermosa, which is beautiful. Okay, good. Hermione, Hermosa. I will try to remember from now on. Stephanie Mesh says, good morning from Germany. Good morning, Germany. Good morning. How are you? Which part of Germany? Frankfurt? That's where I was last time I went to Germany. BJ says, haha, long time no see. South Korea person, BJ, my friend, it has been a long time that I have not seen you, but thank you so much. Tell us some news from South Korea. How about that? Usually BJ always shares something interesting about his country or her country, and it is quite intriguing to hear about. Acacio says Hermosa is beautiful. Once again, I prove to be the better. You do. Honestly, Google Rewrites History has been most excellent in giving us information whenever he joins. It's quite helpful. Whereas my Google Mini, sometimes, once again, I prove to be. I know only landscaping terms in Spanish. Let the H, oh, Hermosa, hour. Let the H in Hermosa is silent, just as an hour. Hermosa, oh, I'm so sorry, I've been saying it wrong. Hermosa? Goodness, I think I'm learning a lot. Everybody, thank you so much for joining. Please do like, share, subscribe. Please do subscribe. Please do double tap and give us some likes. Please do send these hearts and emojis. I love it. Thank you all. Thank you one. Thank you all. Good morning, good evening, good afternoon, everybody. Please do join and don't feel shy. Say something in the chat and don't feel shy. And we will say hi to everybody and catch up, and we will start our topic of the day very soon here, okay? Destiny, hello. Acacio says correct. Sister, the nature, real entertainment, kids in house and animals in house are also, but they can't replace the kids having animals in home, and taking care of them is very good. Hi, Saad. Saad Rashid is saying hi. Hello, Saad. How are you doing? Okay, I am currently making sure. Sorry, but some of us are shy. Roughneck. Hello, Diddy. Hello, Ruff. Need to visit this year, says Destiny. Okay, good recommendations by Destiny here. Some of us are shy. Well, I am shy, and here I am, you know. You can't go wrong. Share something and we will be most appreciative. Okay, let's see. Let me read Saad's comment again. Taking care of them. Thank you, Saad. I think Saad is talking about animals, and I love it. Okay, can everybody please double tap and give us some likes? Thank you so much. Can we have 20 likes? How is the weather down there? Are you talking about in Boston? It's good. It's actually excellent right now. Most excellent. Won't let you down says I love it. Hello, won't let you down. How are you doing? Okay. Like and sub. Let me pin that. Acacio! Thank you for the super chat. There's a bug near me. Acacio says, let's make Windry channel great for once. Acacio, thank you so much. Let me love and like that. Let me heart it and like it. Goodness gracious me. Acacio has done a super chat. Thank you, my friend. Muchas gracias, amigo. Thank you so much. Doing good. What's going on here? So we're about to talk about cosmic rays very soon here. I'm saying hi to everybody. I'm going live after a while, so I'm just catching up with everybody for a minute. But we're about to launch into the topic of particle astrophysics, specifically cosmic rays. Let me say that please do like and subscribe, and let me pin that. Thank you all. Keep the love coming. Sun's coming up in South Africa. Have a lovely day. Oh my gosh, are you from South Africa? Niels Visser is saying sun's coming up in South Africa. Oh my God, that is such a coincidence. I was just now thinking about South Africa the other day. I really want to visit. And here you are. Sun is just coming up in Ireland. Oh my gosh, are you from Ireland? I really want to go to Ireland as well. I think my entire travel bucket list is in the chat right now. Hello, South Africa. Hello, Ireland. Hello, India, America, Brazil, Argentina. Everybody, thank you so much for joining. And hello, hello, hello. Hello, hello, hello. Hello to all. Okay, so now I don't know if you guys know this or not. I'm going to give you a little bit of an introduction to the channel and what we do here. And then we will keep on keeping on. And actually, I totally forgot to share the live. I checked on the settings of the live, but I totally forgot to share it. So let me share it. When would be your trip? When would be your trip to Madagascar? Exactly. Acacio always reminds me to mention Madagascar. I would love to visit Madagascar as well. Thank you. Does anyone know anything about Madagascar? Please do share in the chat if you do. It would be most appreciated. So, without further delay, let's tell you something about physics. If you're here for the physics part, then I do appreciate your patience, and thank you so much for joining. If you're seeing this as a video upload later on, thank you as well for seeing the video and commenting and sharing and all of that good stuff. And by the way, if you have any questions about physics, any subtopics of physics, other than probably condensed matter physics, you should definitely, I mean, even condensed matter physics, you should put it in the chat. If you have any interests related to physics and you want to make a comment or you want to ask a question, please do feel free to put it in the chat or in the comments whenever you see this. Appreciate all the inputs and all the questions. My own background is in particle astrophysics. I have a doctorate in physics, but within the subfield of particle astrophysics. If you go on to graduate school, you might notice that there is no way to get a PhD in particle astrophysics, not that I know of anyways. Generally, you will be enrolled in physics. Generally, you will be enrolled in physics, but then you have to do research in a more specific topic. And for me, that was particle astrophysics. I also did some cosmology. So those two, particle astrophysics and cosmology, are generally heavily discussed on this channel because those are my background as well as those are my interests. I love learning more about each one and discuss it all here with you and do these study with me type of videos, both in the format of shorts, clips, videos, lives, everything. So if you are new to the channel, please do like, share, subscribe. Please join our live streams and hope to see you on the shorts and videos and comments as well. And there is Baji. He does have some siblings, and so pretty much we cover the best things in this world, which is physics and cats, and cats and physics. So, and me, I'm the host. So when did you find out you were psychic? Says won't let you down. I don't know if you're doing a play on words because I said that I do physics, physics, psychic, same thing, I suppose. I don't know if I'm psychic, but I do have a pretty good intuition. Hopefully, maybe I can say something here tonight, which will be about your future. So, so let us now continue. So, why I'm going to talk about cosmic rays tonight is because it is actually a pretty important topic in the overall field of particle astrophysics. As you know, when you go on to become an expert in any type of topic, you become increasingly and extremely focused into one thing, into a very small part of an overall larger field or domain. For me, even though I say my subfield is particle astrophysics, my subfield is radio astronomy, or basically astrophysics done with radio techniques, and then the subfield is to do with neutrinos. So the particle of interest in the particle astrophysics that I did was the neutrino. This is a particle that's very introverted. It's does not interact much with anything, interacts weakly through the weak nuclear force, and is a very low mass. We almost thought it might not have a mass, but it does. It does, but it's just very low mass. So this particular particle, it tends to be very elusive and whatnot, making it quite hard to detect. And so there's an entire subdomain in physics which have to do with these experiments. And then depending on the energy regime of your experiment, whether it's a lower energy or a higher energy or a very high energy or an ultra high energy, you would design your experiment accordingly. And you would be interested in neutrinos from various different sources. Now, we're considering astronomy and astrophysics as the sources here, or sometimes we also call them cosmogenic. So pretty much these are space neutrinos, if you will, to put it simply. These are space neutrinos, as in they come from space. They can come from the sun. That is the one of the closer, I would say, probably the closest source really, where the neutrino is coming through a nuclear physics reaction. Or it can actually also come from other, very importantly, from other galaxies, from far, far away sources, from astrophysical sites where lots of things happen, exotic physics happen, some big explosion or some natural particle accelerator type of physics can happen in certain explosive and extreme environments and events in the sky, which are generally in other galaxies, and neutrinos can come to us even from those. So as you can imagine, there's just a lot of variety that we have here, and pretty much depending once again on the energy scale, where you are in the energy scale, which I kind of showed some energy scale type of stuff in the live stream last time. Depending on that, you would design your experiment accordingly. You would be sensitive to a certain energy of neutrinos, and depending on that, you would be sensitive to a particular type of physics, because depending on if your instrument is not sensitive to a very ultra high energy neutrino, then you're not going to be getting those neutrinos that would be coming from those types of exotic events, and so on and so forth. So neutrinos, in other words, was my sub field that I worked in. And even in my experiment, which was the ANITA experiment, Antarctic Impulsive Transient Antenna, this is the main particle that we were trying to detect. And the whole engineering and science part was to build the detector and build sensitivity towards these ultra high energy neutrinos coming from interesting sources in astrophysics. I mentioned the word cosmogenic, so let me finish that train of thought. Cosmogenic neutrinos, the difference between astrophysical neutrinos and cosmogenic neutrinos is the fact that basically if a neutrino interacts with something along the way, even though we said that it does not interact much, or sorry, not a neutrino, if a cosmic ray interacts with, say, a photon along the way, when it's coming towards us, the cosmic ray itself might have been made in some other process, but then along the way it can actually interact with the cosmic microwave background photons, which we know about as well. And through that type of indirect process, so the direct process didn't have to do with the neutrino, but because the cosmic ray interacted with the photon, through those nuclear reactions, you can basically get, or particle physics reactions, you can basically get a neutrino. So that type of neutrino, which is basically made in a secondary kind of interaction, so you're not getting the neutrino that is from the exact source, but you're getting the neutrino after something from the source has interacted with CMB photons. Those are called cosmogenic neutrinos. So I mean, even a neutrino like that would be pretty interesting if we detected one. But basically, I just want to make the difference, the distinguishment or whatever, that there are neutrinos that are coming directly from the astrophysical site, from say a very high energy supernova, or some other source, for example the sun. But the sun, of course, does not make as high energy neutrinos as some of these other things we're talking about, etc., etc. Those are neutrinos coming directly from the source. But then there are other things. We will talk about those other things tonight. Cosmic rays, I've already kind of mentioned once here. Cosmic rays can interact with things along the way because they are not as elusive as neutrinos. So they do actually interact. And through that interaction, you can get a neutrino. And then if we detect that neutrino, that would be a cosmogenic neutrino. So now, why am I talking so much about neutrinos? It's because that's my background, first of all. And second of all, I wanted to give you some context that there are multiple different types of particles that one can be interested in when you consider doing particle astrophysics. Basically, particle astrophysics, the definition is basically studying astrophysics or astronomy with particles other than light. And really what people mean is with particles other than traditional visible light. Because if you think about astronomy, it's a very old science, people looking up at the sky, and it used to be very dark back in the day, where you could see a lot of stars. And when you see the sky with your naked eye and you see lots of stars, galaxies, planets, whatever, that is basically a part of astronomy done with the naked eye, just picking up on visible light. Because our eyes, because of the shape and the size of our eyes, cannot see light of every wavelength. So when I say visible light, I mean the light that is visible to us and of those wavelengths. Like, for example, we cannot see radio waves because radio waves are larger. Radio waves can be the size of a room, for example, or they can be sort of, I'm doing this, trying to show you about a meter or so. But also this room could be the wavelength of a radio wave, So because our eyes are not as big as a room, we cannot see radio waves, for example. Or X-rays. X-rays are too tiny, so we also don't have the geometry to see X-rays. Okay, so these are various ways of seeing that. Even in terms of light, there is a lot of variety, and we see visible light. We can see the sky with our naked eye and see all those objects in the sky because the visible light from those sources are reaching our eyes, and our brain is processing it, and we are, we're doing something with that information. We are good detectors of visible light. But there are lots of other types of light: X-rays, gamma rays, radio waves. These are all other wavelengths of light. Now, if there were sources emitting this type of light, we would not be able to see it with our own eyes, but we can certainly build detectors that would be sensitive to these other wavelengths of light, including X-rays, gamma rays, radio waves, etc. And in fact, we do that. We have gamma ray observatories, we have X-ray observatories, we have radio wave observatories, we have different types of detectors for all these different types of signal from different sources. So in fact, at this point, we have come such a long way where we can even take a part of the sky and look at it in these different wavelengths, and you might hear about things like the X-ray sky or the radio wave sky or the gamma ray sky. Okay, so those are to give you some variety of the light. Now, basically at this point, not just different types of light, we can also do astronomy or astrophysics with different types of particles. So light is not the only thing that reaches us from faraway sources in the sky. Cosmic rays also reach us from faraway sources in the sky. Neutrinos reach us from faraway sources in the sky. In fact, we even get gravitational waves. So at this point in time where we have started to do multi-messenger, what you might hear of as multi-messenger astronomy or astrophysics, it's not just a light game. It's not just building detectors that can get the light from different sources, but also neutrinos, also cosmic rays, also gravitational waves and whatnot. So for example, gravitational waves was not detected directly until some years ago, and that was a big reach. That was a big goal of ours that was yet not met. But now we have gravitational waves. So guess what? When a detector like LIGO, laser interferometry gravitational observatory, I believe is what LIGO stands for. When a detector like LIGO sees gravitational waves from a faraway source, such as say two black holes colliding, or a neutron star collision, or a black hole and a neutron star collision, which by the way was also theorized to be a source of gamma rays during gamma ray bursts, particularly short gamma ray bursts. So I'm giving you an example directly right now of multi-messenger astronomy. When LIGO picks up on gravitational waves from such an event, like the merger or the collision between, say, black hole, neutron star, we get gravitational waves, right? But from that same direction, from in that same time window or around that same time window, we may also expect to see gamma rays, for example, because we also have this phenomena called short gamma ray bursts. Gamma ray bursts is a transient event in the sky, happens in faraway locations, in other galaxies, extragalactic type of source. And we basically get gamma rays during those transient events. Some of them are short gamma ray bursts, some of them are long gamma ray bursts. This is another whole topic. So now, because we are in the era of multi-messenger astronomy, we wouldn't be satisfied with just getting the gravitational waves. We would also want to see, ooh, did that thing also make gamma rays? So this is where we're kind of going. This is where we are. It's already here. It's already current. And increasing our technologies and increasing our capabilities to do multi-messenger astronomy is going to be very important, because basically you can probe different types of physics in different wavelengths and different how do I say it? Different particle diversity, right? So basically, you can think of it as getting gravitational waves is one level of understanding of that event. Getting the gamma rays would be another level of understanding and a different kind of understanding. So for example, because the lab in astrophysics or astronomy is so far away, it's not like we can go to the black hole collision. Hi, Heike. I just see a Heike here. Hello, Heike. Hello, Joshua. Hello, Eversoar. So we cannot easily, anyways, go to a black hole merger and be like, let me see what's happening here. It's not like how you can work in the lab in other parts of physics or chemistry or biology, where you can really literally take like a sample and look at it in the lab in your hands, right? In the lab locally. But in astronomy and astrophysics, local is very relative, but pretty much by local, we still mean pretty far, right? Like the moon is local, the sun is local, but these things are still very far from us, right? So something like that's really, really quite far away would be very difficult to probe and really understand what is going on at those events and what kind of physics is going on. Because also remember, we understand that our environment here on Earth is is very different from these other environments. The environment that produced those gravitational waves that LIGO picked up on, or the environment that produces gamma rays, is nothing like the environment that we know and love here on Earth, or even in our solar system, or even maybe in our galaxy in some cases. So it's also a way to understand physics more deeply and more broadly when we can look so far away and get different types of particles from from these sources, because that's our information about those sources. So whenever you hear about, if you're ever wondering, like, why does she care so much about neutrinos? Like, why do you even want to get neutrinos from a source or astrophysical neutrino? Like, what's the big deal? We in particle astrophysics want to understand more about our sources, in other words, and more about the physics of those sources. And that's why we want to get what we can get from in every way possible. Sometimes it's through neutrinos, sometimes it's through cosmic rays, sometimes it's light, sometimes it's a different type of light, like it could be gamma rays versus X-rays, that type of thing. So it's literally part of the challenge is that the lab is very far away, and part of the challenge is that it's a related challenge is that we don't experience anything like that. Having said that, I also want to note during this rant that we actually do have particle accelerators that humans made on Earth, obviously. There is the Large Hadron Collider. We have some other ones as well. So we do have particle accelerators here on Earth, right? But we gained inspiration for that from nature. Nature has its own particle accelerators that are much, much more extreme and that produce a lot of radiation that are very luminous. So we have talked about how gamma ray bursts are basically natural particle accelerators that have more luminosity. Like when the gamma ray burst is going off, it has more luminosity than an entire galaxy. So take something like our galaxy, all of the light, all of the luminosity of our galaxy, more than that is when a gamma ray burst is taking place, because it's a transient event, as in it's a short event. It's not something that is a steady source, it's a short event. So there is just a lot of variety in astrophysics. What we're lucky, we're here, we're alive because we are a relatively more boring part of the universe, this galaxy, the Earth, all that. We also have a lot of beauty as well. We have a lot of interesting things about us as well. But a lot of the things that we're interested in, depending on who you are and what type of astrophysicist you are, is going to be very far away, and you want to get all the information possible. So this is why we have multi-messenger astronomy. I also mentioned earlier at one point in an earlier live. So if you go to my live tab of the channel, you will see all the lives. Generally, if the lives are short enough, and by short, I mean they can be really long. Some of my lives are a few hours long. The recordings are all available under the live tab of the channel. So nothing is like going away. You can always find this later on under the live tab. And for you, if you're interested in the older lives, you can go see the older lives, and there's a lot of discussion happening in those lives as well that are all related to this. Physics, cosmology, astronomy, astrophysics, right? So something I wanted to mention, or I did mention earlier, was that the ANITA experiment, which I was part of, Antarctic Impulsive Transient Antenna, we were looking for neutrinos. We are looking for neutrinos in the analysis. Even now, some of the analysis is probably going on. So the main particle of interest was ANITA, okay, or was neutrinos in the ANITA experiment. But the interesting thing was that as a side product, as sort of something that we didn't intend for it to happen, but it did happen anyways, we were actually sensitive to something called cosmic rays, something that we've been mentioning, we're about to mention here tonight. So this is a whole other type of particle that turns out we were sensitive to, that we picked up on, we measured for, and we picked up on the signatures of, and we actually discovered new cosmic rays, like cosmic rays that were not discovered by other experiments, for example. And because this is an ultra high energy experiment and we measured ultra high energy cosmic rays, that is actually kind of a big deal, because measuring these particles at ultra high energies is difficult. We only ever get a handful, like a lot more than neutrinos, but it's not like you have like millions and millions of these. you generally only pick up on some, depending on the experiment. And our experiment wasn't even really intended for cosmic rays, but we also picked up on a handful of complementary cosmic rays. Because also remember that it's always good for multiple experiments to do a type of measurement, because the cosmic rays that we discovered may not have been discovered by other experiments that were intended to measure cosmic rays, because they're looking in a different direction, or they're on for a different time of the year, or so on and so forth. Because remember, there's also real logistics, you know, like Anita flies in the austral summer. So we are on during the flights of Anita, we were on during the austral summer. So in Antarctica, when it's summer during the Northern Hemisphere's winter, is when we would fly the balloon mission, which would have the detector and look for neutrinos during those month or two, you know. And so it's on like live and collecting data during that time, and it's looking at that, you know, southern sky. And it's also because of its geometry, it's sensitive to a certain geometry of particles that come in, and you can see that, etc. So the sensitivities also depend on your logistics, on your design, on your geometry, on your when, where, all of that, right? So it's always good when experiments are in different parts of the Earth and looking probably, hopefully, both in overlapping time windows as well as different time windows, and looking at different parts of the sky and whatnot, because either you can confirm another experiment or you can complement another experiment, okay? Excuse me, Range Rover is saying, what level of maths do you need for your PhD and work? Excuse me. So the math is I'm not sure how to, like, you need a lot of math. So pretty much, let me just say this. So I was a physics major in college, in grad school, all throughout all of my schooling. I've been a physics major, and it's a very math intensive program. So in undergraduate, some people double major in physics and math, because by the time you've taken all the math for your physics, you almost have a degree in math. I personally have a math minor. I didn't do the full major in math because I double majored in physics and chemistry. But the math major has more overlap with physics. So you need at least, I mean, you need all of, you need, you know, a lot of calculus, differential equations, linear algebra. The linear algebra is for quantum. You need statistics, advanced statistics. So you need advanced statistics, all of calculus, linear algebra for quantum, the differential equations series, all of that. Okay, so, and then some more stuff as well. So a lot of people found it to be useful to just get a degree in math as well. So I know people who are double majors, or they have double degrees in physics and math, because of how much math you have to end up taking in physics, okay? But I wouldn't say that it's harder than chemistry or biology, because double majoring in chemistry and physics was hard because there was not as much overlap, and chemistry has a lot more lab time. So like you have these long labs you have to do, right, when you're doing an undergrad in chemistry, and that's not easy either. So it depends on what you find easy or hard. A lot of lab, a lot of the practical applications is more in you know, chemistry and biology, and a lot of remembering things is also needed in chemistry and biology. So you know, physics is a good I don't know, I like it a lot, but yeah, all of them are kind of hard. Jan says, hi from the Netherlands. Hello to Netherlands. Hello, how are you doing? So anyways, I was saying how we were sensitive to the cosmic rays, and we complemented other experiments that actually are interested in and were wanting to discover cosmic rays, and these are ultra high energy cosmic rays. So what are cosmic rays? We will get into this book tonight and give you a little bit of an introduction. Well, probably at least some detail. This is the book called An Introduction to Modern Astrophysics. It's quite heavy, but this is what it looks like. So just to let you know what I'm referencing tonight. So far, the spiel I've been giving is just my own knowledge and experience. So I haven't used the book for that. Just my own research experiences in particle astrophysics is something that I'm sharing from. But for the more textbook information, we will look at this book. Once again, it's called An Introduction to Modern Astrophysics. This is the second edition that I've got. This is Bradley Carroll and Dale Ostley's book. So Carroll and Ostley, it's very famous sort of authors for, for this book. It's an orange colored book in case you're interested. So basically, cosmic rays. This is what we'll talk about tonight. What are cosmic rays? So basically cosmic rays are, it's actually sort of a broad definition. Cosmic rays are simply charged particles that are constantly bombarding us on Earth. So these are charged particles that have been made in various sources, either in an astrophysical source, so an astrophysical site where lots of different things are happening, physics is happening, maybe there was an explosion, maybe there was a supernova, who knows? Things got accelerated, made a cosmic ray, it came to us, we hopefully detected it with some kind of experiment or detector, and there you go, that's a cosmic ray measurement. Or it can also happen in, the cosmic ray can be also made in some other processes, and that type of cosmic ray is coming towards us. And so I said charged particle, literally that's a really broad definition. So any particle with charge. Stephen, what's up? Oh, you're saying you hated math. Oh no, oh no. Harry Puwagianto says, I'm a physics graduate. Hello, Harry, how are you doing? So, given that it's a very broad definition, sometimes what we do is, for the examples, we stick to just charged protons. Like, I mean, protons have a charge, so I don't have to say charged protons, but basically, literally a proton, which has obviously a positive charge, is also an example of a cosmic ray. And depending on which type of cosmic ray and what the interaction of it with the CMB photon is, cosmic microwave background photon is, you can get a series of different reactions and different particles, and sometimes even a neutrino, like I was mentioning earlier, and that could be another source or a way, I don't want to say source, that could be another process of getting a neutrino, okay? Harry is saying, ask me anything about physics. Oh, very nice. So people, you can ask Harry anything about physics, go for it. Eversor is saying, I'm a ufologist. Oh, UFO. Is that a UFO? What does that mean? Harry, welcome. And yes, please do like, share, subscribe, and share your physics knowledge. UFO. Okay, let me share the live once again. Okay, so now let me tell you about cosmic rays from this book, including a bit of a history on how cosmic rays were even discovered, even found for the first time, that is. Is a perpetual motion machine possible? Thank you for liking and sharing. Really appreciate you, Eversor. So I'm not sure that a perpetual motion, actually no, let me say that. Let me think about that. A perpetual, so you know, a free particle, if it wasn't being acted on by anything, and if it's in motion, will just continue to be in motion. So is a perpetual motion machine possible? I mean, I think, X Power is the one who asked that, and Harry is volunteering to build a perpetual motion machine. So I think X Power and Harry, you've got a collaboration going. Now I design spaceships. Oh, let me read that from here. My aim is to design big spaceship to bring 1,000 people to planet that have water. Oh, how nice, Harry. Okay. So why don't you guys discuss about the planet and the perpetual. So I was going to say that that is an interesting thought, but you know what? I'll let you guys discuss. Okay, so going back to cosmic rays from this book. So as old as 1900s, as old as the early 1900s is when cosmic rays were discovered. So let's read. On August 7, 1912, Victor F. Hess, who himself was from 1883 to 1964. So Victor Hess and two colleagues ascended in a balloon to an altitude of 5 kilometers. Earlier, I was mentioning my ANITA project, the Antarctic Impulsive Transient Antenna, which is also a balloon project and balloon-borne mission, and it goes up to an altitude of almost 40 kilometers. So these balloon-borne missions or balloon experiments are not super new. Here we are in 1912 on such a balloon experiment or a balloon mission. So they went up to about 5 kilometers. So maybe back then the balloons didn't go as high, which is fine, you know, makes sense. During that 6-hour flight, so they went to an altitude of 5 kilometers and they were up there for 6 hours. Hess made careful readings from 3 electroscopes that he used to measure the intensity of radiation. So nowadays, we don't go up in the balloon ourselves, you know, but I guess back in the day, they were very adventurous and he went up with it and actually made those measurements himself. As the balloon rose, Hess determined that the level of radiation increased with altitude. So one of the reasons why we wouldn't want to go up is because there is more radiation. Down here, we're kind of protected by the atmosphere and whatnot, and so we don't get exposed as much to the radiation coming in from the cosmos and also the sun. But back then, he just went for it and he went up with the balloon. And he saw what we know now, which is that the level of radiation increased with altitude. From his experiment, he concluded the results of these observations seem best explained by a radiation of great penetrating power entering our atmosphere from above. So this is where he was like, wow, great penetrating power entering our atmosphere from above. This event marked the birth of the study of cosmic rays. So basically, he might have, expected, like, sure, there might be some things from the sun and whatnot, or maybe, let's just see what happens, right? And another thing I also want to mention about balloon projects is that putting something in space, like to orbit around the Earth, like a satellite, is very expensive. But if you're just interested in some altitude, like you just want to go up some, but not necessarily be in an orbit, not necessarily have to make a spaceship or a spacecraft and do all that, and still have some atmosphere to breathe, then a balloon is actually the magnetic field, that's beauty. Yeah, then a balloon is actually very appropriate. It's cheaper. It doesn't cost as much money as to launch and put something in orbit around the Earth like a satellite. You still have some air to breathe if you're on it as well, that is. And you know, you're just you've got a great view. So pretty much I would highly recommend a balloon if you want to go up and up in the sky instead of jumping into a spaceship to be gone forever or to orbit for a very long time. Okay? That might just scratch the itch, if you will. So, charged particles from space, basically 40 kilometers altitude, which is what the altitude of Anita 4 was. That is almost space. It's basically like being in space with a very thin atmosphere without going all the way into space and requiring a lot more energy when you have to basically leave Earth's, you know, gravity and start to orbit, right? So so yeah, anyways, balloon projects can be useful for that. So and pretty much if you're trying to be sensitive towards things that are coming from space, then you're a little bit closer when you're on a balloon mission, right? So this is so because you'll see how different particles that I mentioned in particle astrophysics, depending on neutrinos or cosmic rays, there are different ways of detecting them, and sometimes being up in the air is advantageous because the way you detect them is actually through the air shower, which we will talk about. Okay. Joshua goes too fast. Okay, so although referred to as rays, so cosmic rays is literally two words, COSMIC, cosmic rays, RAYS, cosmic rays, okay? So, although referred to as rays, this penetrating radiation is actually composed of charged particles. A wide range of masses and classes of particles have been identified in cosmic rays, from electrons, positrons, protons, and muons, to a host of nuclei, including but not limited to carbon, oxygen, neon, magnesium, silicon, iron, and nickel, products of stellar nucleosynthesis. So literally, any charged particle. It can be protons, it can be positrons, it can be electrons, it can be a host of nuclei. It can be a host of nuclei of different types, because you can have nuclei of the type of nickel, iron, neon, magnesium. So things that are made in a star, in other words, and then maybe they're ejected and they have some charge, and here they come into the Earth's atmosphere, and they would be regarded as a cosmic ray, okay? Particularly striking is the wide range of energies involved, from less than 10 to the 7 eV, or electron volts energy scale, to at least 3 times 10 to the 20 eV. So we will talk about this energy scale in detail, but look at that. Wide range of energies with which cosmic rays are coming in to our Earth's atmosphere, all the way down from 10 to the 7 eV to 3 times 10 to the 20 eV. So 10 to the 20 eV is ultra high energy. So I mentioned in a previous live, ultra high energy is pretty much defined as 10 to the 17 or 10 to the 18 eV and above. So if you are 10 to the 20 eV in energy, then you would be considered an ultra high energy particle. And I mentioned how Anita has a number of ultra high energy cosmic ray discoveries. So that's the interesting thing. It's not just any cosmic rays that we picked up on, that we discovered or we measured. It's ultra high energy cosmic rays, meaning that where they come from is interesting. Particle accelerators, nature's particle accelerators, that where they may have been created, is an interesting question and something for us to learn more about. Because what accelerated a particle to have that energy, that high of an energy? That's the question. So near the low end of the energy spectrum, so this is the energy spectrum of the cosmic rays impinge on the atmosphere with fluxes of more than 1 particle per meter squared per second. So fluxes more than 1 cosmic ray per square meter per second is pretty high. You know, that's a lot. Like, I'm not saying that, you know, it's not, it's like, I guess it's actually, kind of like, we do say that these are things that bombard the earth, but they're not like neutrinos from the sun, okay? Like, they're not that common. But still, one particle or one cosmic ray per meter squared per second is still pretty high of a flux, whereas the highest energy cosmic rays, so for the lowest energy cosmic rays, the number is one particle per meter squared per second, whereas the highest energy cosmic rays have fluxes that are very low. So this is the thing, if you're going to be going after a high energy or ultra high energy cosmic ray, it's much, much more rare to find them. So what is low? Less than one particle per square kilometer per century. Thank you, Eversoar. Thank you so much. I love that you're enjoying. So, how cool is that? So this will give you an idea that the ultra high energy cosmic rays that we discovered with the Anita experiment are truly very special, because literally the flux, as in how many of them that we get at the highest energies, is literally one cosmic ray per square kilometer per century. So it's very rare. At the lower energies, they're pretty common. You get like a particle per square meter per second. But at the highest energies, literally, you're getting a particle per square kilometer per century. So much, much more rare. And you have to look harder. You have to have very good sensitivity, or you have to just either look for a very long time, or you have to look over a large area, because this square kilometer business, right? So imagine if you were surveying a very big area, then that square kilometer thing, the number would go up. The per century thing, well, hopefully it doesn't take a century, but even if it does, you know, such is life. Physics is just this never-ending field. So the flux as a function of energy is shown. So I'm going to show you this flux plot because it's actually a very famous one. So the cosmic ray energy, the cosmic ray flux as a function of energy. So this is sometimes called, I think it's just, I can't remember. Basically, it's just flux versus energy. Or spectrum, that's what I was trying to say. It's the cosmic, so if you hear cosmic ray spectrum, what they mean is basically the cosmic ray flux as a function of cosmic ray energy, because how many of these things we get is very different at different energies. Namely, you get a lot less at the higher energies, and at the highest energies you get very sharply less, as in there's a sharp drop. So I'm going to show you this plot at the end of the live, okay? I'm gonna leave it on, and I'm gonna show you the plot at the end of the live because I want you to see it. It's a very famous plot. I'm getting distracted by the comments. Thank you guys. I'm gonna read all your comments in a bit too. So I'm gonna read everybody's comments in a little bit, and I'm gonna show you the plot at the end. But anyway, the cosmic ray spectrum is basically flux versus energy. And the main thing is that there's a sharp, steep drop with energy as the energy is higher, okay? With the highest energies, basically, you get so much less cosmic rays. Okay, so the question naturally arises. Now we're going to talk about sources of cosmic rays. The question naturally arises as to what the source or sources of these particles may be. One obvious answer is our sun. So the sun might do some stuff. The sun is part of it. As we saw in chapter 11, of this book, but we didn't really go over it tonight. The solar wind, flares, and coronal mass ejections emit charged particles into space on a routine basis. So we get a lot of stuff from the sun. So that's normal, especially if you go up in the sky on a balloon. You would be exposed to more of that. And I'm not sure how good that really is for you physical, health-wise. And so it's not super recommended. Now what we might do is send a detector up in the sky and let that detector do these types of measurements, not ourselves. So as we saw in chapter 11, the solar wind, flares, and coronal mass ejections emit charged particles into space on a routine basis. Although abundant, these solar cosmic rays, also known as solar energetic particles, are relatively low energy particles as cosmic rays go. So by the way, even though our detector in Anita might have been bombarded with solar cosmic rays or solar energetic particles, those were too low energy actually for us. We're not really sensitive to low energy particles, as in we might get bombarded with them, but our detectors are not going to register them as anything. Or actually, I want to take that back. That's not necessarily the case, that our detectors would not register them as anything. It's just that they would look more like noise to us. That's the better way of putting it. We are sensitive to lots of things. The main characteristic or the main signature, the signal of our experiment would be something quite rare. But then we collect data all the time, or we collect signals all the time, but those are actually noise, right? So the lower energy stuff would be more like background noise for us. And so if you have, interesting things like solar particles in the background noise, maybe that's something, maybe that could be a separate analysis of like, okay, go into the background noise and, some of it might be thermal noise, some of it might be anthropogenic noise, like human-made noise, some of it might be sun particles. So like that could be another analysis, but that's not the main signature that we were after, but I'm sure that there was probably some of that. So anyway, recall that the fast solar wind has ion speeds on the order of 750 kilometers per second. So apparently the solar wind, I always say how I actually don't know too much about our sun. It's always from this book that I learn more about our own sun. I have never researched our own sun. I just know limited information. But okay, so the fast solar wind has ion speeds on the order of 750 kilometers per second. I mean, I guess that's pretty high. For protons, this corresponds to an energy of 3 keV. So around 3 keV, to me, that's hella low energy. See, I worked with EeV, that is the 10 to the 18 EV and above. So like keV is something like I've never seen. Like in my scientific, career, that's so low energy, I've never dealt with it. Just saying. Even in energetic coronal mass ejections, when protons may travel at a speed of around 0.1 c, where the c is the speed of light, the energies are only on the order of 10 MeV. So you can be going at a pretty high speed of 0.1 c, but the energy of you would be 10 MeV at those levels, or from the coronal mass ejections and stuff from the sun, right? See, this is why I said that we live in a relatively boring part of the galaxy or the universe, because we're near a sun that's making stuff or ejecting, crazy particles. Like the craziest ones are only like 10 MeV. Whereas, my experiment was looking for stuff that is EeV and above. So like orders of magnitude more energetic than stuff that come out of the sun, for example. Because the sun is not just giving us light and heat, it also ejects these types of particles, the ones we're talking about. It's just that my experiment was interested in particles like that, but of much, much more higher energy, which would be made in sources or events very different from our sun. Our sun is a good it's a good boy star. It's not doing anything too crazy. It's not time for it to do anything too crazy anyways, which is why we're alive. So that's good. The sources of higher energy cosmic rays have been identified with supernovae. So supernovae is a star's death. Our sun is young. Hopefully it will not be dying. And so that's why we don't get, supernova is a much more explosive, much more extreme event and environment, once again, which can maybe accelerate particles to these types of energies, to the higher energies. It happens when a star is close to its end of its life cycle, and it dies. Yes, Betelgeuse. So Joshua is saying if Betelgeuse goes nova, so Betelgeuse spelling is Betelgeuse. So Betelgeuse, if it goes supernova, then the cosmic particle rays will bombard us exponentially. Yes. UV ray is a type of light. Am I saying that right? Ultraviolet? Yeah, it's a type of light. So we're not talking about light from sun. We're not talking about the light particles or the photons from sun. Literally, we're talking about charged particles. So like the sun, so light as in UV rays, X-ray, radio wave, those are all still light or electromagnetic waves. We're talking particles, like charged particles, protons, other nuclei, literally just some stuff that's ejected out of the sun. But the energies, like the highest energy ones from the sun, are still only around 10 MeV. So that's pretty low compared to the particles that we were interested in an ultra high energy experiment, but just to give an idea. But anyways, so the sources of higher energy cosmic rays would be things like the supernovae, like I was saying. Supernovaes, okay, interesting. The sources of so this book is saying the sources of higher energy cosmic rays have been identified with supernovae. So before energy of 10 to the 16 eV, so less than equal to 10 to the 16 eV. There is a knee. So you will see in the plot in a moment here, there is a knee in this figure at between 10 to the 15 and 10 to the 16 eV. So this knee is what they're calling, that's probably due to the supernovae. At such high energies, the speed of the particle is essentially c, and the rest energy is negligible. For a proton, mc squared is 937 MeV or a GeV. Consider the radius of the orbit of cosmic ray particles about the magnetic field lines in the region of space in which they find themselves. So another thing to note, contrary to neutrinos, cosmic rays are charged particles, and so they are affected by magnetic fields. Hello, Justin. It's called conditioner. What's up with your hair? Okay, thank you so much for being here. Like really, really small dust in layman's terms. Sure. Yes. Sure. Yeah. You could think of it as really, really small dust. I would say, so like dust is a lot bigger than these particles. Like we're literally talking about like fundamental particles. Like a proton is much smaller than dust. You know what I mean? But sure, dust is pretty small as far as, something to compare with. So you could think of that. Like you could think of that. But also another thing in which this is different is that it's being ejected out. It's being like spewed out with some energy. So it's not just like a passive, oh, there's some dust on me type of thing. It's like being spewed out. And depending on the source or the event, it will have more energy or less energy. Conditioner and Ozempic. we should talk about conditioner at some point and the chemistry of conditioner if you're interested, TX Justin. But, and Ozempic, actually don't know what exactly is the chemical formula. Actually, TX Justin, while you're at it, can you tell us the chemical formula for Ozempic? And tell us some chemistry. But I think you're interested in chemistry more than physics, which is totally fine. Totally fine. Which is I support it. I support it. I support chemistry talks as well as physics. So I have no problems. In fact, I was a double major in physics and chemistry, and I loved it, but physics probably a little bit more. So consider the radius of the orbit of cosmic ray particles about the magnetic field lines in the region of space in which they find themselves. So we know that cosmic rays will be affected by magnetic fields because they're charged and they cannot escape the electromagnetic type of interactions like neutrinos can, because neutrinos do not have a charge and they do not interact with electromagnetic type of stuff. From the Lorentz force equation, if we neglect any contribution from electric fields, the force on a charged particle in a magnetic field is Fb equal to Q Vb, where Q is the charge, V is the velocity, and B is the magnetic field. So as you can imagine, if there are magnetic fields that the charged particles have to navigate or come across as they make their way towards us on Earth, they will be affected by those magnetic fields. In fact, magnetic fields can bend them and can significantly disturb the trajectories of these types of particles. So this is a big difference. So we want to pause here for a moment and appreciate that this is a big difference between cosmic rays and neutrinos. Neutrinos only interact with the weak nuclear force. Any interaction that neutrinos will do with other things is through the weak nuclear force. It does not interact with the electromagnetic force or with electric and magnetic fields. So neutrinos are not bent by magnetic fields along the way when they come to Earth. Cosmic rays do interact with magnetic fields because of their charge. They're charged particles of various types, and they can absolutely get disrupted by magnetic fields, and their trajectories can change and bend because of magnetic fields. So when you see a cosmic ray, depending on the circumstances, you may not be able to point back to its source because it could have been bent along the way, okay? So that is a very interesting difference between cosmic rays and neutrinos and how they vary and they act differently as messengers of astrophysics. UFO. Steven, yes, we need to see your book. And then Justin is telling me something about teeth. We should get into biology. In fact, can you give us the chemical formula for teeth while you're at it? Give us some chemistry. What is teeth? Give us some chemistry of teeth. You know, it would be nice if you shared more information, TX. By the way, TX always reminds me of transmission. RX is receiving, TX is transmitting. So TX, why don't you transmit some more details and information? Don't be so surface level. Don't be so surface level. Calcium and what else? Tell me more. Tell me more. Don't be so surface level. In fact, can you tell me, okay, tell me the atomic number of calcium. Tell me what process makes it in the stars. And what else can you say about chemistry of teeth? So for the special case where the velocity of the particle is perpendicular to the magnetic field, you would basically have QVB as the force that's on a charged particle, because remember, it's really V cross B, if I remember correctly. It's been a while, but the force on a charged particle of charge Q due to a magnetic field B, where B is a field and B is a vector and V, the velocity of that particle, is a vector, is V cross B. So V cross B is not going to be QVB unless V and B are perpendicular to each other. Aman, how are you doing? Do you see Baji behind me? Aman loves Baji. There is little Baji baby. So let's keep going. Since the Lorentz force is always perpendicular to the direction of motion, the force is centripetal and results in a circular path. So it's interesting. Since the Lorentz force is always perpendicular to the direction of motion, the force is centripetal and results in a circular path of the particle around the magnetic field. Isn't that so cool? This implies that gamma mv squared over r is equal to qvb, where gamma is the Lorentz factor. Solving for r, the Larmor radius, that is LARMOR, or the gyro radius of the orbit for such a force would be gamma mv over qb. So for this special case, one second. Why is it not telling me what that equation is? It's okay. For the special case where the velocity of the particle is perpendicular to the magnetic field, we have this. And because the Lorentz force is always perpendicular to the direction of motion, the force is centripetal, and we basically get this circular type of motion. So when we put V equal to approximately C in that equation of the Larmor radius or the gyro radius, we actually get R to be gamma mc squared over QCB, which is E over QCB. So we can even simplify that further. Hi, Distance. Hi, Aman. Durga Puja? Yes, happy Durga Puja. I gotta go live in the afternoon again. Okay. So we think that cosmic ray particles with energies below about 10 to the 15 in the year 1912, August 7th, discovered cosmic rays for the first time by going up on a balloon, quite literally, to about 5 kilometers altitude. So the cosmic rays that have energy of about 10 to the 15 eV are possibly associated with supernova remnants, is what we think. But once their energies exceed that limit, they escape from the remnant. It has been long suggested that the shock waves associated with supernovae could be sites of acceleration of cosmic ray particles. So this is what I was talking about when I said nature's particle accelerators. Certain very explosive, extreme types of environments in nature, like a very, very big supernova or a gamma ray burst or something like that, can actually accelerate particles, or so we think. When we see the particles from such sources and we confirm them and whatnot, then that's a confirmation of that type of physics where you basically accelerated a particle to a very, very high energy. Enrico Fermi was the first to propose a mechanism by which supernova could accelerate charged particles to ultra-relativistic energies. So Enrico Fermi, basically this is called the Fermi shock waves or Fermi acceleration. This is where basically these particles are, there's a mechanism, there's a process happening within the supernova material layers and actually even a gamma ray burst environment material layers. And the shock, Fermi shock acceleration can happen where the particles get accelerated to ultra relativistic energies. He suggested that charged particles trapped in magnetic fields can be accelerated to a very high energy through successive collisions with the advancing shock wave. So it's not just a little bit of acceleration, because there are successive collisions. Oh, really? Oh, how nice. Really, that's awesome. So Range Rover says, that's my paper. Fermi was a condescending dude. Oh, really? Was he? He is my great, great, great PhD grandfather. He's in my academic tree. So, so it's not just a little bit of collision, it's a lot of successive collisions that can happen in these environments within the material of that supernova when the supernova is happening. See, some stuff expands, some stuff is falling back in because of the gravitation, etc., etc. So there's an explosion, in short, plus there's also infalling matter. These types of things, which I'm not explaining in detail right now, basically can lead to a lot of successive collisions and where particles are accelerated a lot, like a lot. So that would be the Fermi shock waves or Fermi shock accelerations. After absorbing energy from the shock, a particle is accelerated forward in the direction of the shock motion. Think of an elastic collision of a particle with an advancing wall. However, being tied to the magnetic field in the shock's vicinity, the particle is forced to return only to collide with the shock again, receiving additional energy. So it's almost like it's already accelerated, and that's why it was moving like a lot and with a high energy, but the magnetic field is keeping it trapped, so it just gets accelerated even more. So the particle is forced to return only to collide with the shock again, receiving additional energy. The process is repeated many times until the particle possesses sufficient energy to escape the bonds of the supernova's magnetic field. So it's almost like Jim Brenner is saying, very impressed with your knowledge on this subject. Well done. Thank you, Jim. How are you doing? Please do like, share, and subscribe. We talk about this a lot. So once again, the Fermi shock waves or the Fermi shock acceleration is not just about something being accelerated once due to a collision. It's a repeatedly colliding due to material that's been expanding and some of it infalling in these layers, and the collision between the layers, right? And also charged particles being trapped by magnetic field, forced to kind of stay and get accelerated again and again, is what's causing this level of acceleration. So once again, this is a natural particle accelerator. It's much more powerful than the ones that we built here on Earth so far anyways. And so ultimately, at some point, some of the particles, after attaining so much energy, will actually break free from that environment and can get spewed out and basically come here towards Earth. And unless it's been disturbed along the way by some other magnetic fields, we can see them, and we can see them with these high energies. So an important thing to note about when we see ultra high energy cosmic rays or ultra high energy neutrinos or whatever, is that they were made in very extreme environments, like they went through these types of processes, like not only extreme environment of a star or a supernova, but within that extreme environment, something very extreme happened to them, which is the Fermi shock acceleration, which is theorized anyway, and whatnot. So when we see, say, particles or neutrinos or whatever coming with such high energy, ultra high energy, those types of ultra high energies were not attained normally, if you will. They went through something very specific. So it's almost like we are seeing a cosmic ray here, but it has this history of like all this crazy stuff that happened to it not only because it came from a very extreme environment, but more extreme things happen to it in that environment. Okay? So the power law nature of the cosmic ray spectrum, it goes as F proportional to e to the minus alpha, is characteristic of this non-thermal source of energy for these particles. So it's a power law, and it goes as a non-thermal, or it goes as a power law, and from that we know it's a non-thermal. It's not really a ordinary type of interaction or process that's making these things have that much energy and following that type of power law in the spectrum. An X-ray image of supernova 1006 obtained by Japan's advanced satellite for cosmology and astrophysics suggests strongly that supernova remnant shock fronts are indeed the source of acceleration of cosmic ray particles with energies below about 10 to the 15 eV. So if you have a cosmic ray of 10 to the 15 eV or below, then we do think, hi JG, how are you doing? This is actually not pre-recorded. I am here in the live with you guys. Hi Jim. Jim said, I will from British Columbia, Canada. Hello, Jim. Oh, JG was asking if this is pre-recorded. No, it's not pre-recorded, but sometimes I do have videos coming out that are pre-recorded. This one, no, this is a live. So because we actually do also spend a lot of energy and time studying supernovae, for example, this particular one, SN1006, and because of the X-ray images from that supernova by Japan's advanced satellite for cosmology and astrophysics, we actually have the suggestion that this supernova remnant shock fronts. So we basically have more evidence that yes, there is a supernova. Yes, there is shock fronts. And yes, we get cosmic rays. Like basically, the more information about an event, the better. The more information that you get from something like a supernova or something like a different transient event, gamma ray burst or some other thing, the better. Yes, you want to get the gamma rays. Yes, you want to get the X-rays. But if you can also get neutrinos, if you can also get cosmic rays, then you would understand, then you would confirm whether these are sources or these events are where particles of that nature get accelerated or not. And then this Fermi shock wave thing, for example, this is a theory, but to kind of get the confirmation and understand it better as to exactly what is happening in those types of environments, we actually need to get these detections of those different particles. At least we can get help when we do detect those particles. So pretty much that's where it remains unclear where the highest energy cosmic rays come from. So even though we have at least a handful, if not at this point more than a handful, I think there is in the hundreds of ultra high energy cosmic rays, but I could be wrong. You should look this up. I think we have in the hundreds of cosmic rays at this point that are ultra high energy, but please do verify that because I'm kind of recalling something and it's not from the book. So even though we have quite a few of them, but you know, not millions or billions of them, quite a few of them, we still don't fully understand them. We have some good theories. And part of it is that we have some theoretical predictions associated with some of these particles. But then we actually will measure things with real experiments and real detectors. And once we get the measurement and once we get the actual signature of like what that looks like, then we can actually compare it to the theory and see whether the theoretical predictions are being confirmed or being constrained. So for example, if a theory tells you that you should have seen this many cosmic rays, but then in experiment you actually see fewer, then what you do is you say, well, this theory is actually being constrained by our finding. It predicted too much. So something about the theory has to be revised, has to be updated. And then the theorists too take that into account and they're like, yeah, actually, you know what? I think on this step, I miscalculated or I assumed something. Actually, it's not about miscalculation. It's more probably about an assumption, because when you're doing theories, when you're coming up with a theory of something that is so far away and so extreme and so different from our own environments, of course, there's sort of a challenge there, and there are assumptions being made that you might have to revise. So it's actually very common to constrain theories, and it happens through these experiments. Okay, so that said, it remains unclear where the highest energy cosmic rays come from. From the existence of the Ni above 10 to the 15 eV in the cosmic ray spectrum, it appears that the source of higher energy cosmic rays is fundamentally different from the supernova source below 10 to the 15 eV. So we don't think that the ultra high energy cosmic rays, in other words, is coming from the same source. In addition, the ankle near 10 to the 19 eV suggests yet another source for the most extreme cosmic rays. So we think that the most energetic or the most extreme cosmic rays have a different type of source. And it's all coming from this spectrum, the flux versus energy spectrum of the cosmic rays. It has been proposed that the cosmic rays with energies between the knee and the ankle may be due to acceleration in the vicinity of neutron stars or black holes, which would be really cool if we confirm that. On the other hand, the most energetic cosmic rays may originate from outside our galaxy, possibly from collisions involving intergalactic shocks, or perhaps from the active regions in the centers of most galaxies where supermassive black holes are believed to reside. Hi, Ilias. Play a song for me. You should make me mod. I would have dealt with him much earlier. Thank you. Let me make you a mod. Thank you, Eversore. Eversore is now a mod. Thank you so much. Acacio is #1 top fan, followed by Francis, followed by Won't Let You Down, followed by Steven, followed by Parabolic Curvature, Range Rover, Joshua. Thank you so much, everybody. Ilyas is saying, oh God. Is Ilyas the same as TX Justin? Well, well, well. Okay, so, well, hello to everybody. Thank you so much for being here. Can we get some likes, some shares, some subscribes? Streaming a long time today. Yeah, I'm just going through the material. So, we will look at the plot that I've been referencing. But basically, the plot shows different fluxes at different energies. Hi, Skeletor. And it has certain interesting features which we associate with basically different methods or processes of making the cosmic rays that we're seeing here on Earth. If you see, sort of a different kind of flux at a certain energy than at another energy, we can say that maybe these energy cosmic rays are made in a different process than those energy cosmic rays, because the flux is totally different. So these types of things, even a simple plot like flux versus energy, even a simple plot like flux versus energy can tell us a lot about, at least about like, okay, maybe there are this many different processes. But of course, keep in mind that to actually get that plot, you have to collect the data, you have to collect maybe years and years of data, and you have to, you know, populate the plot further in order to like start to say things. But at the same time, if it's been some years, if it's been say like 10, 15, 20 years, and you keep populating the plot and you keep getting more and more points where you would kind of expect, then you start to see the pattern, right? And this is kind of what happened here. BJ is saying, actually, I'm not interested in Korea. Oh, then what are you interested in, BJ? Are you interested in physics? Javier is saying, don't do it. Don't do what? So anyways, it seems like we don't fully understand where the ultra high energy cosmic rays are coming from. We do seem to understand that they are coming from a different source than the around 10 to the 15 EV or the PeV range cosmic rays, which seem to come from supernovae. Okay, so lastly, so I'm gonna look at the comments and see if there were any questions that I didn't answer or missed, or something important that I missed, and then I'm gonna show you the plot. I'm gonna show you the plot that we've been talking about, showing the flux versus energy of the cosmic rays and the cosmic ray spectrum plot. So we will look at it. I will point things out from it in just a little bit, but before that, I'm gonna take a little break, stop talking, and look at your comments and see if I missed anything important, or if you have any questions, put them in the chat right now. And thank you for all the comments today. I saw a lot of things kind of go by, and if I missed your comment, hopefully I'll catch it. And if you want to say something or say something again so I see it, go for it right now. Thank you, everybody. This is Baji. The Baji and Physics Baji is right here. So this channel is called Baji and Physics because we talk about cats. We show cats and we talk about physics. So thank you so much, everybody, for being here, and for all your questions, comments, chat messages, etc. And for showing all the love and doing all the likes and emojis and likes and shares and subscribes. Thank you so much. Aman says, off-topic question, when will Baji come live? Well, Baji is live right now. If you want to say something to him, he is right there. But you want to see a Baji special live. I'm so glad you have mentioned it. We will do that very soon. It's good for me to know what you're interested in, and thank you for bringing it up. Thank you for bringing it up, Aman. It's very good for me to know what you're interested in. We try to do these physics lives at least some of the time so that I can continue to push out the videos and the shorts and everything associated with them. And then we also do the the kitty cat specials. So hopefully soon, very soon. Play a song for me. Earth is round. He's super cute. Hi, Maya. How are you, Maya Stamatova? How are you doing? Maya Stamatova. I really like that username. How are you doing? Light under clouds isn't proof, but it is a point. Light under clouds. Okay. Interesting. So, Eversoar, all the comments of the person talking about mustache and whatnot and not giving enough chemistry context, is that the same as the flat earther in this in the chat? I'm just curious. Let's see Earth from space. We have. Is physics more than chemistry? Depends. Don't read them to yourself. Oh, you don't know? I thought you figured it out somehow. That's okay. Don't read them to yourself. Meaning what? Hi, Skeletor. Are you 7-Eleven or the comments? Range Rover, hello. Eversoar. Let me go over here and read them. You think it's CGI? How very interesting. Talk about the universe expansion. It's hard for me to grasp that concept that everything that exists is taking more and more space. Yes! So the universe is expanding and there is more and more space and void between us and faraway things. Very true. So the expansion of the universe is a more large scale feature. Over the largest scales, we have an expansion of the universe and actually an acceleratingly expanding universe. So Acacio, we will talk about that next time, soon. Good for me to know that you like cosmology and would like to learn more about the universe. So let's do that next time. I don't wanna do that tonight because it's already kind of late and I'm kind of tired and it's a favorite topic of mine. So thank you for requesting that. No, not expanding faster than light speed. Cosmetology? No, it's cosmology. There is not real picture of Earth. It's not a theory. It's real. There are real pictures of Earth. We've gone to the moon and seen Earth too. It's like a little blue ball in the distance. Okay, not flat, like a ball. Cosmetology is the study of makeup, something that people are saying I might want to put on. So cosmetology is the study of cosmetics, makeup, hair, I don't know, Ozempic or something. But cosmology, very close, but not the same. Cosmology is the study of the cosmos and the universe and its expansion and dark energy, dark matter, origin of the universe, Big Bang, nucleosynthesis. Those all fall under cosmology, as opposed to cosmetology. Javier says sorry. Oh, sorry about what? You don't need it. I know I was kidding. Oh, you were kidding. Oh, well, a friend of mine the other day actually asked me in all seriousness if I do cosmetology. So I what do you call? I don't mind. I don't mind talking about the differences. I quite like talking about cosmology, and if I have to distinguish it from cosmetology, no problem. Let's see. Javier says, oh, okay. So, thank you guys. You guys have been most delightful tonight. Honestly, even the hate comments tonight were kind of okay. They weren't too bad. Like I half wanted to like just let it be, but then it was too distracting at one point, so I put the person on timeout. But for the most part, tonight has been very nice. Everybody has been so nice and supportive and liking and sharing and subscribing, hopefully. And all the comments have been very, very nice and engaging. So I really love it. Thank you guys so much. Maybe because you have good skin. I have good skin? Well, why thank you. Well, thank you. Thank you. Oh, God. The hate was kind of suave. Ilyas, are you quite all right, honey? What is wrong with you? Okay, any other questions and comments? Any other questions, comments, thoughts, requests, recommendations, criticisms? Let me know, my darlings. Oh, your friend asking you if you're in cosmetology because you have good skin. Oh, thank you. Thank you very much. And thank you, God. Thank you, universe. And thank you, genetics. And thank you, biology, chemistry. Thank you, monkeys, where we come from. Thank you, indeed, evolution. Thank you, universe, indeed, for your help, support, protection, blessings, kindness, and guidance, and good skin. Scooby-Dooby-Doo, where are you? I was attending your live stream while also being in my office meeting. Multitasking, Aman. Wow. Can you sing the Chili's song, Baby Back Ribs? Scooby-Dooby-Doo, where are you? That's the only song I know at this time. We did not come from monkeys. Did we not come from monkeys? Oh, please do tell me where we came from then. Are we not? Oh, do you mean that we are monkeys? I agree. We are a type of monkey. Wow, you have a pretty voice. Do you guys want me to hear, or not hear, sing a song? Imagine all. What is that song again? Imagine by John Lennon. Is your Space Mountain your favorite ride? I don't know. Imagine. Yes, a Hindi song. Aman, what request do you have? Hindi song? What shall I sing, Aman? Aman is the one who has been requesting Hindi songs. Imagine there's no heaven. It's easy if you try. With full emotion. No hell below us. Above us, only sky. With cosmic rays. Imagine all the people living for today. Woo-hoo. You may say I'm a dreamer. Wait, is that? That is the words, yes. You may say I'm a dreamer, but I'm not the only one. We didn't come from, we were... Once Upon a Time in Mumbai. I don't really know that song, Aman. Hope someday you'll join us and the world will live as one. Hopefully you liked my song today. Monkeys were also created. I don't want YouTube to imagine Indribi without her nice smile. Monkeys were also created. I'm glad you said created. যদি তোর ডাক শুনে কেউ না আসে তবে একলা চলো রে। Aman Arora. Song request. যদি তোর ডাক শুনে কেউ না আসে তবে একলা চলো রে। একলা চলো একলা চলো একলা চলো একলা চলো রে। যদি তোর ডাক শুনে কেউ না আসে তবে একলা চলো রে। Despacito. Hi, Jason. We're a type of primate with opposable thumbs, nonetheless. Absolutely. I thought we are a type of primate, which I called a monkey, with opposable thumbs. Was Jimmy Neutron your favorite show when you were younger? I was not allowed to watch TV when I was younger. We did not have cable, so I do not know what you speak of. I do not know what this Jimmy Neutron is, and I don't know what it is. Indeed, I do not. I grew up without the cable, and we only watched a few DVDs of certain movies from Bollywood in my home on Sundays only. That is it. No shows allowed. Was that Persian? No, it was Bengali. My mother tongue is Bengali. Can you sing Eminem? I do not know. Such a soothing voice. Thank you. He's a boy genius. You speak very posh. You haven't even answered anything I said. What have you said, my darling? Rollbot, it is a children's cartoon. Damn. I'd still kiss you. Play a song for me. Typical Indian families. Removable cable, same here. I mean, it was removed permanently. Quite permanent. The removal of cable at my house was quite permanent. It never came back. I left. Cable is still gone. What's your favorite tea? Darjeeling tea.